Hi everyone, welcome back. Today we're going to be looking at power series. Now what I want you to do is I want you to recall back when we were looking at geometric series and what it is that we were identifying with that geometric series. We identified a few things about a geometric series. One of those things was that the geometric series does converge when the absolute value of the common ratio is less than 1. And it diverges for any values, absolute values of that common ratio greater than or equal to 1. Now, we then said, well, if the geometric series is convergent, then it will converge, and it will converge to this formula right here, which is a, that first initial term, divided by 1 minus r, where again r was that common ratio that we were initially observing. So I want you to hold on to this piece of information because the way we're going to develop a power series, or better yet, the way that we're going to be talking about a power series is going to have a direct relation to this geometric series that we essentially started observing. All right, so what I want to do then is I want to then start looking at a certain polynomial. All right, so let's look at, let's loof. All right, let's look at a polynomial, call this f of x, which is going to be 1 plus x plus x to the power of 2 plus x to the power of 3 plus, and let's make sure this goes to some n value, plus x to the power of n. So this should remind you of some polynomial that we've kind of seen back in an algebra class. All right, so this shouldn't be too new to anybody. Okay, now looking at this polynomial here, I can actually express this polynomial as a summation, right? If we take the index starting at, let's say, 0 and stopping at n, then what we can say here is that we were looking at x to the power of the index. In other words, x to the power of I. If I is 0, then that means we get 1 because x to the power of 0 is just 1. X to the power of 1 is just x. X to the power of 2, x squared, so on and so forth, all the way till we get to the final term, which is x to the power of n. Now, this is what I want to be looking at here, because now what I want to do is I want to consider a very similar polynomial now. So now let's consider, let's call this g of x, right? This is going to be a different polynomial. Even though it's going to look very similar, it's going to be different. So now this polynomial, I'm not going to have a stopping point here. In other words, I'm going to be looking at this polynomial heading towards infinity. Now, could I still represent it as a series? Well, sure we can. Right? The series now, at this point in time, now changes just a little bit for us. All right? So what I'm going to use as my index here is I'm going to switch back to an index of n. Let's say n starting at 0. And this is going to be heading towards infinity. Now, first term was just 1, that's fine. And then the common ratio here looks like the common ratio that we were initially working with, which just looks like x to the power of n. Now, again, n is the index, so n tends to infinity, which means this polynomial will, again, keep going towards infinity. Just keep on repeating itself infinitely. Now, why am I discussing this? Well, I'm discussing this because at this point in time, both of these values are geometric series. So both of these series are geometric series. Now, the first one, yeah, I kind of don't want to, let's say I'm not going to put too much attention to the first one in a bit because I only want to focus on this one, the one that tends to go to infinity. This is going to give me more information as to what it is that I'm going to be dissecting. All right, so let's talk about when this converges. So g of x converges when its absolute value of the radius is less than 1. But what's the absolute value of the radius? Well, converges when the absolute value of the radius is 1, but x is that common ratio that we're looking at. So what does that mean then? Well, that means for us that the series converges when the absolute value of x is less than 1. Well, algebraically, so equivalently, this means that this is going to converge whenever x is less than or equal, whenever x is larger than -1 or less than 1. All right, so that's pretty cool so far. Now, this is when it converges. Also, if it converges, then g of x, which is this series here, 0, there we are, x to the power of n, is equal to the convergent formula that we have. But what is a? In other words, what is a beginning value? The first initial term. That's just 1. Divided by 1 minus r, but what's r? That's just x. Which means that g of x has a representation, and not only does g of x have that representation, but g of x was this power series that we were looking at, or this geometric series that we were looking at. If the geometric series converges, and it only converges for these values, then it will converge to this formula here. Now, that's very beneficial, because what I want you to do then is I want you to then analyze this. Check this out. If we eliminate the middleman here, it says that g of x has this formula 1 over 1 minus x, which means it has this representation as a series. Now, what does that mean for us? Well, let me give you a visual representation of this. All right, so in order to give you a visual representation, I'm going to go over to Geogebra. So follow me along. All right, so we're here on Geogebra now. Now, what I want you to do is I want you to then start analyzing this here. So, I went ahead and I took a function, I called it f of x, which the function was 1 over 1 minus x, which is that function that we were initially looking at, that g of x function, right? Now, I'm looking at my series input here. Look at my series input here. So on my series input here, I just have x to the power of some n value, where n is the index as my series is going to be running through this. All right, so here I'm going to have n is equal to 1. There we are. So what I did here, or what I developed here, was I developed this series here that as long as I'm expanding this slider, this series is just going to start generating those terms. Now, what does it mean to be convergent or divergent in terms of a power series? Well, let's start checking this out. So if I take n is equal to 1, meaning I only have one term here, or two terms, 1 plus x, then that means I'm just left with a line, and this line is at 1 plus x, right? Where y is equal to y is equal to 1 plus x. That means my y-intercept is 1 and a slope of 1. Now, what happens if I slide it over to x is equal to 2? Now I have this parabola where I have these three terms, n is equal to 0, n is equal to 1, and n is equal to 2. This now gives me this polynomial for x squared plus x plus 1, and that polynomial is then here. If I generate a third term for that series, and again, this is that geometric series that we were looking at, generating a third term now gives me a degree 3 polynomial, and this is that degree 3 polynomial. Now, what I want you to do is pay attention to what that degree 3 polynomial is actually doing, right? Watch this little piece right in here as my mouse is hovering over it. This blue line, which is my power series, is actually kind of like what we're doing, pasting it on to this green curve, which is my function of 1 divided by 1 over x. Now let's slide it to 4 terms. So check out what's still happening. It's becoming a closer and closer model for that green line. In other words, that 1 over 1 minus x. Now, if I keep increasing the terms, check it out all the way to 10 terms, then I have almost a perfect match beginning here and kind of moving off to this side. So it's kind of like we're putting on some wallpaper on here, right? We start peeling the wallpaper and then we start putting it on and it starts becoming one with the wall. And that's kind of what this is doing. The power series is kind of becoming one with the function. All right. Now, n is equal to 10. Yeah, still not good enough, right? Not good enough. All right. So what I'm going to do is I'm going to extend this over to 100 and we're going to see what happens here. All right. There we go. All right, so I'm going to just slide this over to 100. Now, look at what's happening for this little piece here. Notice that as x, or as the power series is approaching -1, it can't make up its mind. It's saying, hey, I'm going to drastically go down below, or I'm going to drastically move up top, like such, right? Which means there's some type of bound here. And if you remember from what we were talking about when we started this section for power series, we said that this geometric series, specifically for x to the power of n, only converged for the x values between -1 and 1. So, what does converge mean then in terms of a power series? Convergence in terms of a power series means that we are able to model this with a certain function. But we will only be able to model it with that certain function on a given interval. And what it is that we need to do is we need to find what interval will this work for. Will it work for -infinity to +infinity, meaning that we're always going to be able to model this function with this power series? Or will it mean that it's only going to work for some random interval, which might not be so random, like this one is from -1 to 1. All right, so we now have to develop our talk into that. When are we going to be observing a convergence, and when are we not going to be observing a convergence for this specific polynomial? All right, so that's what we want to see here. All right, let's go ahead and there we go, start that animation. So again, as your n value increases, you get a better approximation to that function. All right, but as you don't increase your values, then sorry, that means we're not going to be getting a good approximation for this. And that is how we're using this power series. All right, so now that we saw this visual representation for this power series, let's go back and let's start actually defining this a little bit more clear. Alright, so what I'm going to do is I'm going to start defining this a little bit more clearly. And again, here was that convergence ratio, or that convergence value between -1 and 1 for this function. So let's go ahead and let's write out the definition for the power series. Alright, so here's the definitions that we're working with. The first definition says that a power series about x is equal to 0 is a series of the form, and that's going to be that power series form that we were initially looking at the very beginning. Now, a power series about x is equal to a is a power series of this form. Now, that form should kind of remind you of some sort of maybe binomial formula that you've kind of seen back in an algebra course, maybe a trig course. All right, so we can definitely tie all that in at a later time. Just again, know that it should resemble it. And all of this is using center of A and the coefficients C0, C1, C2, all the way to C sub n. And then going forward from there are all just going to be constants. Now, theorem. We're going to have a theorem here. This theorem is going to say that given a power series, there are only 3 possibilities. All right, now that's kind of kind of like a misnomer or something that is misleading where it has these three possibilities. And I'll explain why in a bit. Alright, so for the first possibility, we have that the series converges whenever x is equal to a. Now, if x is equal to a, then we're going to make that insertion here, x is equal to a. Then that means at this point in time, we get this term to be 0. 0 times the constant is just going to be 0, which means this series is just adding a whole bunch of zeros, which again, convergent. So, number 2, the series converges for all x. Now, that's kind of like what we were looking at on this example, the one that we started with, that power series representation for 1 divided by 1 minus x. That representation here for this power series did not converge everywhere. Alright, it only converged for some values. Now, if there was some function that we could model using a power series that has no limit on convergence, well then that series will then converge everywhere for all x's, meaning that we won't need to see this part here. The interval of convergence will then be negative infinity to infinity. And then the last one, and here's that troublesome part. So there's a positive number r such that the series converges if the absolute value of x minus a is less than r. In other words, this middle term right in here, this x minus a, that what we were calling that common ratio for the geometric series, that only converges if it's less than some r value and diverges if it's greater than some r value. Now, for part 3, there are 6 different outcomes for part 3. And this is where I said it was kind of misleading, because there are only 3 outcomes, and these are the 3 outcomes for this theorem. However, part 3 breaks down into some more different outcomes. The different outcomes are here. If we can find the interval of convergence, or the radii of convergence, then we need to extract the endpoints as well. Will the power series converge for the endpoints? Alright, and that's what we need to be looking at. This first example, it does converge for the endpoints, therefore we use a bracket to denote inclusivity. The second example right next to it on the right does not converge for the point on the right in here. It only converges for the point on the left, the interval, and that's it. We use a parenthesis to denote exclusion here on this interval of convergence. Same thing for this one down here, third example down below the first one. Alright, here we have that this series does not converge for the left endpoint, but it does converge for the right endpoint. The fourth example says that it does not converge on the endpoints, therefore it only converges on the interval. Alright, so this is kind of like that first example, that 1 over 1 minus x. The next one is that it converges everywhere. Well, that's kind of nice, converges everywhere. It boils back down to this part here. Still falls under this example there. Alright, and the last one says that it converges for all x. So converging for all x, the last one says that converges only at x is equal to a. So x is equal to a is this first example here. The series converges when x is equal to a. So these are all of the 6 different possibilities that we actually get from this specific theorem, where the last 2 are just the first 2 here. Alright, so this is what we're having to look at, and what we always want to do is we always want to test the endpoints. So I'm going to write this as a note. Always test the endpoints of the interval of convergence. Alright, this is going to let us know whether they converge or whether they diverge at the endpoints. Alright, so let's go through a first example just to get our feet wet and see how we're going to be using this power series that we've just developed. So here goes your first example. We want to determine the radius of convergence So determine the radius of convergence and interval of convergence for the following power series. So here goes the first one, part A. We're going to have a power series, let's say n beginning at 1, for negative 1 to the power of n. This is going to be multiplied by n, and then divided by 4 to the power of n, multiplied by x plus 3 raised to the power of n. Alright, so here we are. We now need to determine what is the radius of convergence. So in here, this is actually telling us that, hey, given this power series, we know it's going to converge, but now all we need to do is figure out on what interval and what is the radius of that convergence that will be taking place. Alright, so what I'm going to use here is I'm going to use the ratio test to see when this is going to converge. Alright, so let's go about using that ratio test. Alright, so here I'm going to say L, which is going to be that limit that we are initially trying to observe with that ratio test. Let me actually go a little bit higher. Is going to be the limit as n tends to infinity, and this is going to be for the absolute value. You know what, I'll leave that line out. For this function when we have n plus 1. So this is going to be negative 1 to the power of n plus 1 multiplied by n plus 1 divided by 4 to the power of n plus 1 multiplied by x plus 3 raised to the power of n plus 1. Now remember, we need to divide this by a sub n. In other words, the formula using the n values, this formula. But if we're going to divide it by that, and this is a fraction, that means we just multiply by its reciprocal. Its reciprocal in this particular case is just 4n divided by, oops, let's make that a little bit nicer. 4 to the power of n divided by negative 1 to the power of n multiplied by x plus 3 to the power of n. And again, this is all in the absolute value. Now again, remember, that's because we're dividing by a sub n, and just multiplying by its reciprocal is the same thing as dividing by the initial function here. Alright, excuse me. Alright, so let's go through and let's cancel a few items. Alright, so notice we have an absolute value. Therefore, when we have the absolute value, this negative 1 to the power of n plus 1 is going to be obsolete for what we are looking for. Alright, so that's not going to be too bad. And again, we'll elaborate as we go through here. So let's keep going. Limit as n tends to infinity. Absolute value. This is going to be negative 1 to the power of n times negative 1 to the power of 1. Remember, same base multiplying, we add the exponents. Multiplied by n plus 1, multiplied by x plus 3 to the power of n plus 1. All divided by 4 to the power of n times 4 to the power of 1, multiplied by 4 to the power of n, all divided by negative 1 to the power of n multiplied by x plus 3 to the power of n. And actually, I could simplify this right here. My apologies on that one. Let's cut this one for now. And there we are. And I'm going to do x plus 3 to the power of 1. There we are. And then I can insert what I cut. There we are. Perfect. Awesome. Now, you're going to see that a lot of stuff is going to cancel here. So negative 1 to the power of n, that's going to cancel negative 1 to the power of n. We're going to have 4 to the power of n, that's going to cancel out. We're also going to have x plus 3 to the power of n, x plus 3 to the power of n, that cancels out. And then I'm not seeing anything else that can directly cancel out here. So I'm going to rewrite what I have here. So the limit as n tends to infinity. And this is going to be for the absolute value of this initial piece here, which is going to be negative because of this negative 1, multiplied by n plus 1 times x plus 3. There we are. All divided by 4 times n. Nice. That doesn't look too bad at all. Now remember, I'm using the absolute values here, and I'm also going to be using the fact that this limit only considers n values. Now, because that's going to be the case, then that means anything that's a constant can move outside of the limit. So the 4 is a constant here, because again, it's a multiple constant, and we also have x plus 3 to be a constant. So in here, x plus 3, let's rewrite that 3 a little bit better. So x plus 3 is a constant when taking a limit as n tends to infinity. And again, it's only a constant. We're assuming it's a constant, or we're treating it as a constant because the limit only operates on n values. And in this particular case, x has nothing to do with this n value. So let's go ahead and let's apply that then. So, oops, excuse me here. So constant-wise, we now have 1/4, and we also have x plus 3. And then we also have the limit as n tends to infinity. And again, absolute value means that this negative goes away, which means we have n plus 1 over 4 to the power of n. Now, what is this limit going to converge to? Well, we'll figure it out. Multiply both numerator and denominator by 1 over n. So that's 1 over n, that's going to be 1. 1 over n here, that's going to be just 4. And 1 over n here, that's going to be just 1 over n. This is going to tend to infinity. This tends to 0, which means the limit here, we should only be left with the 1/4. All right. All right, here we go. Now, I just realized I factored out a 4th, and I kept the 4th in here, which does not make sense for us. All right, there we go. Now, this limit here should be 1, which means since this limit here is 1, then that means we only get 1/4 multiplied, oops, and I made a big fudge. The reason I made a big fudge here is because I forgot to include the absolute values on the x plus 3. Remember, x plus 3 here, x plus 3 is inside of the absolute value. Therefore, when we factor it out as a constant, we must carry that function that was being operated on it, which was that absolute value function. So this here we get x plus 3, there we go, absolute value of x plus 3 multiplied by 1/4. Now remember, this is our limit here. All right, now the ratio test. The ratio test says that this limit L converges if it's less than 1. So if this limit is less than 1, by the ratio test, it will converge. It diverges if L is greater than 1. So Actually, I will do this in green as kind of like a note. By the ratio test, the series will converge if L is less than 1 and diverge if L is greater than 1 or L is L equals to infinity. All right, so if it's greater than 1 or if it tends to infinity, then we get that the series will diverge. Now, what does that mean for us if we're trying to find a radius of convergence? So, the series will converge, and this is an absolute convergence. Absolutely. Again, absolute convergence because of the ratio test. So the series will converge absolutely when the absolute value, or sorry, when 1/4 times the absolute value of x plus 3 is less than 1. In other words, this L value, that limit value, L must be less than 1 for convergence to occur. Therefore, L, that limit that we took, must be less than 1 in order for this to converge. All right, so that's kind of nice for what we get now. Now, what does that mean for us? Well, what that then means is that we get the absolute value of x plus 3 must be less than 4 in order for this to converge. Awesome. What does this tell us? This actually gives us the radius of convergence. This is right here. Radius of convergence. We oftentimes call this R, capital R. Capital R is equal to 4. All right. So, once we have this, all right, let's go ahead and let's now find that interval. All right, so the interval of convergence. In order to find this, we're going to be using the absolute value of x plus 3 is less than 4. And we're just going to use algebra here. What does algebra tell us about the absolute value less than some number? Well, it tells us that it must be greater than its negative version, negative 4. And less than 4, and we're going to subtract 3 on both sides. So subtracting 3 gets us negative 7x, and it gets us 1. There we are. So this is the interval of convergence. So interval of convergence so far. All right. Now, I said so far because at this point in time, remember what I said as your important note right up here. Look at the note in red. It says, note, always, 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 always test the endpoints of the interval of convergence. Well, if we have the endpoints of the interval of convergence, we need to test the endpoints. Now, you might be saying, Mr. Castro, why do we need to test the endpoints? Well, there's one more outcome for the ratio test. What's the final outcome for the ratio test? If L is less than 1, it will converge, series will converge. If L is greater than 1 or tends to infinity, then we get that the series will diverge. But what happens if L is equal to 1? Well, if L is equal to 1, then what we actually get is the endpoints. Now, check this out. What would happen here if I were to say L is equal to 1? All right, so if L is equal to 1, then we naturally get from this piece here that 1 is equal to 1/4 times x plus 3, which means multiply by 4, then that means 4 is equal to the absolute value of x plus 3, which means that x plus 3 must be equal to 4, or x plus 3 is equal to negative 4. This means that x is equal to negative 7, or x is equal to 1. Guess what these guys are? Those are the endpoints of your interval of convergence. Now, because L is equal to 1 on the root test says that, ratio or root test says that it is inconclusive. Inconclusive means that it cannot tell you whether it does converge or diverge. And for us to be able to bypass that inconclusivity, or inconclusiveness, there we go, to bypass that inconclusiveness, we need to go into testing the endpoints. That's why we have to test the endpoints, because it's a last scenario where L is equal to 1 on the ratio test. And this stands for the ratio or the root test. So now that we have this, we have to test those endpoints. So I'm going to write here, test the endpoints. All right, and the endpoints that we have here, the endpoints are going to be when x is equal to negative 7 and when x is equal to 1. Those are the two endpoints that we need to test. All right, so here we go. So I'm going to say use the endpoint of x is equal to negative 7. All right. So using the endpoint of x is equal to negative 7, we're going to make sure that substitution occurs on the original formula. All right. So when I say test the endpoints, I mean plug them into the original formula. All right. So I'm going to write this here. Plug into the original formula. All right, so here goes. N is equal to 0. Sorry, was it n is equal to 0 or n is equal to 1? I can't remember now. Oops. N is equal to 1. That's all right. There we go. N is equal to 1, tends to infinity, looking good. All right, so then we have negative 1 to the power of n multiplied by n, all divided by 4 to the power of n, multiplied by x plus 3. Now x plus 3 in here, so x plus 3, that's going to give us negative 4 to the power of n. Now again, remember, we're using that x is equal to 7. So x is equal to 7 means that x plus 3 is equal to negative 7 plus 3, which is negative 4, and that's what we get right in here. Nice. All right, let's keep simplifying then. Let's keep it simplifying. There we are. All right, so in here I have a negative, and then I also have a 4. So what I'm going to do is I'm going to separate these two right in here. So this is going to be negative 1 to the power of n multiplied by n divided by 4 to the power of n. And then I'm going to split this. So I'm going to split this in the sense, I'm going to say negative 1 to the power of n multiplied by 4 to the power of n. Notice this is still our algebraic techniques, because in here negative 4 is really negative 1 times 4, and exponents distribute over multiplication for bases. Now if this is the case, then that's kind of nice, because what we're left with here, notice 4 to the power of n's, they're going to cancel, and then we have two of these values, negative 1 to the power of n. So negative 1 to the power of n at this point in time is now going to give us negative 1 to the power of 2n multiplied by n. Negative 1 to the power of 2n, well, this term here, negative 1 to the power of 2n, is always going to be positive. So I'm going to say here, let's do this in orange. that negative 1 to the power of 2n is always going to equal 1. It's always going to be positive, which means if it's always going to be positive, then this here, this series, just gets us the series for n. Now, as we start looking at this, all right, so all we're doing is just adding all of these values from 1 to infinity. Now, we can use a divergence test, and the divergence test says, hey, let's go ahead and check out the limit. So, using the divergence test, so use the divergence test, for the limit as n tends to infinity for n, and this is going to be infinity, which is not equal to 0, therefore this series is divergent. Thus, this series is divergent. So, at the endpoint for x is equal to negative 7, will it converge or will it diverge? That's going to tell me that it's going to diverge. Therefore, this endpoint, this inequality at the endpoint for negative 7, stays as a strict inequality. It does not get the equal sign because it will not converge at that endpoint. All right, so we got that down. Now let's go ahead and let's use the other endpoint, x is equal to 1. So now, use the endpoint, x is equal to 1. And again, we're going to go through the exact same process now. Well, I'm going to be inserting this into my x plus 3, so this is going to be 1 plus 3, which is just going to be 4. Not too bad. Alright, so now I have a summation, n is equal to 1, negative 1 to the power of n multiplied by n divided by 4 to the power of n multiplied by, in this case, 4 to the power of n. And that's where this 4 comes in, simply because we use a substitution for x is equal to 1. Now, if that's the case, again, the 4 n's are going to cancel. And in here, we are now left with negative 1 to the power of n multiplied by n. Awesome. So, all we need to do now is determine, does this series converge or does that series diverge? Alright, so once again, you can use the alternating series, anything like that, anything that we've developed so far in this previous chapter, we can use as our advantage. So use the divergence test once again to see that the limit as n tends to infinity for negative 1 to the power of n times n does not exist. And since it does not exist, it is not 0, thus negative 1, the series for negative 1 to the power of n times n, in this particular case, again, it's divergent. Now, since the series diverges at both endpoints, that now cements in the fact that this interval of convergence that we were looking at the beginning is the correct interval of convergence for this series. So I'm going to summarize all that now. Therefore, the radius of convergence for the series n beginning at 1, negative 1 to the power of n times n divided by 4n multiplied by x plus 3 to the power of n is the interval from negative 7 to 1. And I'm using open parentheses because, again, the endpoints do not converge. Since they do not converge, therefore the interval is an open interval from negative 1 to 7. And the radius of convergence is r is equal to 4. Now remember, that radius of convergence we actually got from this piece of information right up here. So top right hand corner right now, you see the radius of convergence here, r is equal to 4. We were able to extract that. So we were able to finalize and say this is our radius of convergence, and this is going to be the interval of convergence that I'm going to be looking for. All right, therefore the interval of convergence for this series is this interval, and the radius of convergence is this. There we are. All right, everybody, so that's part A. That was only the first example. Now, as you can see, this is a lot of work. A lot of work just to determine what is that interval of convergence and what is that radius of convergence for all of these power series. All of these power series are going to be this intricate, this detailed. So when you're doing this on an exam, I need to see all of these details on there. I need to see, are you using the ratio or are you using the root test to figure that out? And to answer your questions, if you have it, yes, you can use the ratio, and yes, you can use the root test to be able to make this determination of when does this power series converge. All right. Now, once you get that convergence, and that's going to be nice because then that now builds your radius, and that radius now gives you that interval that you need. All right. So awesome. Once you're able to do that, you're going to then run through all of the techniques that we've learned previously, whether it be a comparison, limit comparison, geometric, power series, harmonic, partial sums, anything that we've developed to determine whether a series converges or diverges, we now need to use for these endpoints. All right, so you must be very versatile with this. Now, just a heads up. All right, now, if everyone is using the exact same technique in the exact same way, then that to me tells me that somebody is sharing exams, and that means that there will be a discrepancy in which some people might earn zeros on their final exam, if that's the case. So, please attempt all of these using the different techniques that you have learned previously. All right. Now, we're going to attempt a part B at this point in time. So now, what I want to do is I want to look at a, let's say, different example to try to determine whether this is going to converge, diverge, and to find that radius of convergence that we're going to be observing. So here goes your example. Part B. The summation for the series beginning at n is equal to 1 all the way to infinity for 2 to the power of n divided by n multiplied by 4x minus 8 to the power of n. All right, let's start there. All right, so here we go. So what I want to do here is I want to use a ratio test to determine convergence. So going in here, this is going to give me L is equal to the limit as n tends to infinity. And again, I'm going to use this 2 to the power of n plus 1 divided by n plus 1 multiplied by 4x minus 8 to the power of n plus 1, and then I'm going to multiply by the reciprocal of what I would divide it by, which in this case is going to be n divided by 2 to the power of n times 4x minus 8 to the power of n. And again, you need to make sure that we're using the absolute values here, because when we use the ratio or the root test, we need those absolute values in there. Now, simplifying this as much as we can, the limit as n tends to infinity. Let me see, the two n's are going to cancel. All right, that's going to be good. 4x minus 8 to the power of n, that's going to cancel. And what we're going to be left with here is going to be the limit as the absolute value of 2 times n. All right, that's going to be 2 times n times 4x minus 8 to the power of 1, all divided by, let's see what didn't cancel out here, that n plus 1. There we are. And again, this is all within that absolute value. Anything that's a constant, I could then factor out. So constant-wise, my constant here, I have a 2, and I also have a 4x minus 8. So factoring that out, I'm going to be left with 2 times the absolute value of 4x minus 8. And again, the absolute value needs to be here because it's initially inside of the absolute value for this 4x minus 8. So we have it here, times the limit as n tends to infinity for 2n divided by n plus 1. And again, I drop the absolute value here for this 2n divided by n plus 1 simply because this is always going to be positive for any n value greater than or equal to 1. All right, awesome. So, oops, oh my goodness. There we go. I keep on keeping the constant while I factored it out. My apologies. So at this point in time, this limit will evaluate to be 1. Therefore, we only get 2 times 4x minus 8, exactly like this. All right. So again, here I'm just going to say really quickly, limit as this goes to infinity, this just equals to 1. And we're left with this. So again, at this point in time, this is my limit L. And using the ratio test, well then the ratio test is going to converge if this is going to be less than 1. So the series will converge when L is less than 1. In other words, two times the absolute value of 4x minus 8 must be less than 1 in order for this to converge. And it will diverge if it's greater than 1. So that's kind of nice to see. Awesome. So let's go about this now and let's start extracting what it is that we're going to be looking at when we're talking about this radius. So I'm going to simplify this a little bit more. So let's go ahead and let's simplify it just a little bit more. I'm going to have 2 times the absolute value of 4 times x minus 2. There we are, is less than 1. Factor out that 4, multiply it, that's going to be 8, and then divide both sides by that. Means that we're going to be left with the absolute value of x minus 2 is less than 1/8. Nice. So this is the radius of convergence. Which in this case is r is equal to 1/8. Nice. So we got this radius of convergence, which is 1/8. So we'll keep that in our back pocket. We'll use that to summarize. But at this point in time, again, I want to find my interval. So finding my interval just takes a little bit of algebra work here. I'm going to add 2 to this, 2 to both sides. So when I add 2 to both sides, 2 plus 1/8 gets us 17/8. And then adding 2 over here, 2 minus 1/8 should get us 15/8. There we are. Yes, perfect. Yeah, 2 times 8, that's going to be 16. 16 minus 1, that's 15. Perfect. All right, so there we are. Now we have this interval of convergence so far. All right, so yeah, that's a bad arrow. There we go, and this is my interval of convergence so far. Now again, this isn't the final interval, this is just the interval of convergence that we found so far. We need to test the endpoints. So let's go through and let's start checking these endpoints to see what's going to occur at the endpoints. So right now I'm just going to say use the given series to test the endpoints. And the endpoints that I'm talking about is x is equal to 15/8 and x is equal to 17/8. All right, let's go ahead and let's use it now. So my first one I'm going to be using is going to be x is equal to 15/8. There we are. So x is equal to 15/8. I'm going to go ahead and I'm going to plug this into my original formula. All right, so using my original formula, this is going to be 2 to the power of n divided by n multiplied by 4 times 15 over 8, that's my x value, minus 8 to the power of n. Let's simplify this. Is equal to 1. This is now 2 to the power of n divided by n. So now we're going to simplify this a little bit more, and we're going to be able to extract here. So this is going to be 15 divided by 2, so that's going to be 15 halves minus 8. So 15 halves minus 8, that should get us negative 1/2. So this is going to be negative 1/2 to the power of n. There we are. Not too bad. All right. Now that we have this, let's go ahead and let's simplify it a little bit more, because I kind of see some stuff that will cancel. Some of these terms will cancel. So I have 2 to the power of n divided by n multiplied by, this particular case, it's going to be negative 1 to the power of n divided by 2 to the power of n. And this 2 to the power of n now cancels. There we are. Which then just leaves us with this series. Negative 1 to the power of n divided by n. Now, does that look familiar? It should look familiar from previous sections. This is your alternating harmonic series. Yay! The alternating harmonic series converges from the previous work that we've done. All right, so the series will converge when x is equal to 15/8. Because of the harmonic series. Nice. All right. So far we found that it is going to converge. That tells me that this endpoint, the one that I just used, 15/8, is going to be inclusive. So I need to add an equal sign here for this inequality. So it's going to be less than or equal to. Awesome. I'll keep that in my back pocket. Now I'm going to look at x is equal to 17/8. And we're going to see what's going to happen here for 17/8. All right, so let's start looking at this. N is equal to 1. This is going to be 2 to the power of n divided by n. Oops. There we go, divided by n. And this is going to be 4 multiplied by 17/8 minus 8 to the power of n. And let's go ahead and simplify this. N is equal to 1. This is still 2 to the power of n divided by n. And this is going to simplify 4. That's going to be a half. So 17 divided by 2, subtract 8. That should be 1/2. So this will be 1/2 to the power of n. And again, we're going to get some terms here to cancel out, some coefficients. So the ones that are going to cancel out, let's see, this is going to be just 1, because it's 1 to the power of n, and this is going to be 2 to the power of n. So 2 to the power of n's cancel, and we're just left with the harmonic. Look at that. And what does a harmonic series do? The harmonic series diverges. So the series will diverge when x is equal to 17/8 because of the harmonic series. Oops, I meant alternating up here, because of the harmonic series. My apologies, everybody. Harmonic series. My apologies. This one should say alternating, so what I'm going to do is I'm going to use this because of the alternating. There we go, because of the alternating harmonic series. There we are. Awesome. So again, the first endpoint that we checked, by the alternating harmonic series, it will converge, and the second endpoint, that 17/8, will diverge because of the harmonic series. So now let's go ahead and let's summarize all of this. Therefore, the interval of convergence is, and in this case I'm going to say 15/8, and again inclusive all the way to 17/8, and 17/8 is not inclusive, and the radius of convergence is r is equal to 1/8. And again, r is equal to 1/8, that's what we kept in our back pocket over here, and this is what we're looking at. Now, alternatively, you could have written this interval as x less than or equal to 15/8 less than 17/8. You could have written it this way, and that's perfectly fine. All right, so long as you're telling me the interval of convergence, what it is. Tell me what it is and how you are finding that interval. Awesome. All right, so let's go ahead and let's start looking at a different value or a different example. That way we can get our feet wet a little bit more as to how these are converging, diverging, so on and so forth. All right, so let's try this example C. So example C, this is going to be the series at n is equal to 1 for x minus 6 to the power of n divided by n to the power of n. We're going to see what's happening here. Now, again, we always have to develop, or we always have to find whether it's converging or diverging, and by a certain method. So in here, I'm going to say use the root test to find the convergence. Okay, so again, that's now telling me, hey, I'm either using the ratio or the root test. You are more than welcome to use either one of those tests to figure out if it's going to converge or diverge, or to find what interval that will be converging for or diverging for. All right, so in this case, I want to use the root test. So here we go. I'm going to have L. This is going to be the limit as n tends to infinity for the nth root of this formula here, and that's, or the absolute value of that formula, which is going to be x minus 6 to the power of n divided by n to the power of n. All right, there we are. So now we're going to keep going. All right, so let's go ahead and let's apply that root. So we get the limit as n tends to infinity. Applying the root here gets us the absolute value of x minus 6 divided by n. There we are. Now again, all I have to do is figure out what is a constant and what is not a constant with respect to this limit. X minus 6 is a constant, so I'm going to keep x minus 6 out here with the absolute value, and this is going to multiply the limit as n tends to infinity for, this is going to be 1 over n. And I'm dropping the absolute values here because n, or this function 1 over n, is going to be positive for all values greater than or equal to 1. In that particular case, it just then gets us limit as n tends to infinity for 1 over n. This actually tends to 0. Is equal to 0. Which means in here we get the absolute value of x minus 6 multiplied by 0, we get 0. Okay, so what does then that what does that then tell me? Well, that tells me one thing. The ratio test, or I'm going to say since convergence for the root test happens when L is less than 1, the series converges for every x value. Now, why is that? Well, because our choice of x here, the choice of x will always produce a 0 because the limit for 1 over n will always get a 0. So in this particular case, it doesn't matter what x value we choose. We can choose x value to be negative 100, negative 1000. We could choose an x value of 0, 6, 5, 3, 10, 100, 1 million, whatever it may be. The x value does not matter. This will converge regardless of what x value we choose. Therefore, this limit is in fact 0, and by the root test, when it is 0, it's less than 1, therefore it's going to converge for every x. So how do we summarize this then? The interval of convergence is negative infinity to infinity. And the radius of convergence is r is equal to infinity. Now, could you have given me that interval in a slightly different way? Sure. You could have given me that interval as such. X is unbounded. And again, because x is unbounded, that means we get to choose the values of negative infinity to infinity because it is unbounded. All right. So this is how we're using power series, and this is how we're using these intervals of convergence to determine what interval is it going to converge for and what is that radius of convergence. Now again, ultimately, what does convergence mean for power series? It just means that we'll be able to model a function using power series. All right, so I hope you all enjoyed this lesson, and I will see you all for the next one.